Welcome everyone to the ITC lunch. The last one before the Thanksgiving holiday. So next week we will not. We will all be giving our thanks. We will not meet, but we will meet 2 weeks from now for the last meeting of the semester. We just had an excellent ITC colloquium with lots of questions by Clare Dobbs, who's over there, and she will tell us some more about her work, something that she didn't have in her simulation, magnetic fields indeed. Also today we have a cancellation of the original speaker of the Sackler lecture, Ray Weiss, who got the Nobel Prize in Physics this year. He doesn't feel very well. He had a cold, so he couldn't come today. And on a very short notice, Ido Berger agreed to fill in, and although he doesn't get the Nobel Prize this year,
he's always next year.
And he will talk about the latest exciting event where an electromagnetic counterpart was detected. As many of you saw, last night there was another posting on the archive of another event detected by LIGO in June. That was an event involving the lightest black holes so far, 7 and 12 solar masses. So today we'll start with Pierre Christian, who will talk about what can LIGO tell us about Milky Way LISA detections. Then we'll move on to hear from Clare Dobbs, who will tell us about magnetic fields in spiral galaxies. And after that, we'll hear from Merav Opher, who is a professor at BU that is spending a sabbatical at the ITC this year. She's over there. And she will tell us about constraining the interstellar magnetic field by understanding the draping around the heliopause. If you want to know more about the heliopause, stay tuned, because Merav is the world expert. And finally, we'll hear from Anastasia Fialkov, who is very generous helping us organize these events, and she agreed to the invitation to speak today. So Anastasia will talk about constraining cosmological fast radio bursts. So we'll start with Pierre.
Well, it's my pleasure to be here today, and if you are here, earlier this semester I presented some results on works that disobeys general relativity, and now it's my pleasure to present something on something that obeys general relativity. It's also greatly my pleasure to present this work because this is a work I did with Avi, and Avi had been hosting these events for many years, and no one ever presented his work. So what I'm going to talk about is what can LIGO tell us already now about LISA detections, in particular locally in the Milky Way. First, LIGO binaries are very exciting because, one, they are very massive, and also they are also very tight. There are these constraints causes people to generate a lot of ideas regarding on the formation of these binaries. One of the ideas is dynamical binaries, this idea that in a dynamical cluster, you have black holes interacting and tightening their orbits and producing these very tight binaries. The second idea is the binaries in isolated evolution. These have many different models underneath it. There is the common envelope model in which the stars share their common envelope phase. There's also a model in which the stars rotate very quickly and actually contracts and does not share a common envelope phase. So today, what I'm going to talk about is Sun's population synthesis models. Without any reference to population synthesis models, what can we actually already say about populations of Milky Way binary black holes just based on LIGO detection? So here are the questions that I want to answer. One is, what is the abundance of tight binary black holes that is tight but not tight enough to enter the LIGO band yet in reasonable timescales? Number two, can these binaries be observable by LISA? Number three, are any of these binaries in the Milky Way? And number 4, in what way are binary black holes like a fluid in a pipe? Okay, so certainly here I don't really need to show this plot, but I'll show it anyway. This is the gravitational wave spectrum. So what this actually shows, so what I want to show here is the difference in LIGO and LISA binaries. In general, LISA binaries have, it has lower frequencies. And therefore, if you have a binary black holes of the same mass and it's in LIGO, the same mass, binary black holes of the same mass will be in the LISA band if it's further apart. Okay, so here's the common picture of a binary black hole evolution. Suppose you have a binary with semi-major separation A. This binary generates gravitational radiation, and so there is an E dot that is negative. This means that the binary orbit shrinks into something that is less than A. Now, the shrinking of A dot is given by this equation, dA dt. If you're not in the field and you're curious on how you get this equation, it's actually fairly simple to derive, and you can find it in many GR books. But the first time it is derived is in 1963 by Peters and Matthew, and this is actually part of Peters' PhD thesis. So this is the citation as a function of time for Peters' 1964. And you can see back then, there's like basically no citations, and it ramps up quickly. It takes 40 years. So if you have a paper that you've written a long time ago, back when the universe was neutral, and it doesn't have any citations, maybe in the future it will have citations. Okay, so how does this population analysis work? For illustrative purposes, let us consider first binary black holes that are almost in a circular orbit. However, this formalism is actually generalizable to eccentric black holes and more complicated evolution. If I have a box, I call it A. This is a box where all binary black holes of semi-major axis A lives. There is a diffusion of black holes going through this box. Okay, black holes that are separated by larger than A because of gravitational wave evolution is going to enter A and then leave. Okay, this can be written in a diffusion equation. So suppose my primary variable is rho, the density in A space, in semi-major axis space. This can be written, the evolution of rho can be written in A space as a diffusion equation. Okay, this is exactly the same as this equation. It's just this guy. This k over A cubed is the velocity in A space. That's this equation. Okay? So k is just this combination of numbers. It's like 1 over A cubed. And we add s, which is like some arbitrary source function. Okay? So imagine this as a fluid in a pipe. This is just a diffusion equation. There is a pump at infinity that pumps black hole fluid into this pipe, and there is a sink at A equals 0. Okay? And note there is an 1 over A cubed profile. So actually this is a nozzle. Okay? With some caveats. The flux, what is LIGO merger rate? The LIGO merger rate is the flux across that line there. If it passes that line, that it enters the LIGO band. LIGO rate is just the flux across that band. So it's just a diffusion equation, so we can solve this. For the sources, the homogeneous solution, the solution for rho is just given by A cubed times some function, some explicit function of that combination there. However, we can ask what happens in a steady state case. In a steady state case, it's just A cubed over K. So what is steady state in this sense? Steady state in this sense means that the flux across the LIGO band, aka the LIGO merger rate, does not change with time. This is the standard assumption of the LIGO collaboration. When we have better data, we can relax this condition, but not yet. Now we just assume that if you measure the LIGO rate today and you measure it, 10 years from now, it's the same. Okay? Now, so you have this constant C, which is an integration constant, which you can solve using the LIGO rate, using the fact that the flux across this red band there is the LIGO rate. Okay? So I can assuming all my masses is 30 solar mass, I can already calculate how many black hole binaries there are in the Milky Way. You can plug in the galactic LIGO rate and you get a number that looks like this. Okay, this means for binary black holes with semi-major axis that's separated by about 10 solar radii, there's about a few hundred binary black holes. Again, this is for M1 equals M2 equals 30 solar masses. Now you ask me, what about the source function, we know that black hole binaries are created by stellar evolution. So what happened to the source function? So now, all source functions, well, most source functions have a minimum injection scale. That means that sources cannot be generated under a certain semi-major axis. You can model this by just setting a source function that is proportional to a step function. You can do the integral, and you get something that looks like this. This is the homogeneous solution. This is the extra term based on the source function. However, this term is proportional to a step function. So under this minimum injection scale, which is true for Lisa binaries and LIGO binaries, this term is just 0, and you just get back the homogeneous solution. Okay? Now you ask me, what about source functions without the minimum injection scales? There are exotic source functions. For example, there is one that's, that Avi actually wrote a paper on, in which it can arbitrarily generate sources at arbitrarily small semi-major axes. Sure, we can have that, but also all source functions must have a maximum cutoff scale. Okay, otherwise it's not a binary. It's just like two guys. Like, anyway, so you just have this source function here, and we model this as an exponential cutoff. And if you do this, then this is your source function. This is, again, the source solution, homogeneous solution, and then you have this term here. However, for the source function with a maximum injection scale that is much, much greater than the semi-major axis that we are interested in, these gamma functions, this difference in gamma function actually becomes 0. So what I'm saying is that this naive sourceless homogeneous solution is actually very, very robust. You can use this A cube R over K solution throughout. Okay? Now, those are for black holes with the same. Remember, I was doing that calculation for black holes with M1 equals M2 equals 30 solar masses. What happens if you have a population of them, a population of M1 and M2? So what happens is this. This K, this number that tells the velocity of the black hole fluid through the nozzle, actually depends on the masses of black holes, M1 and M2. In particular, what happens is, instead of having one single pipe, you actually have many, many pipes, each one of them corresponding to a certain value of M1 and M2, a certain value of K. So what we need to calculate here is f of K, which is the probability density of K, of this velocity. Basically, like, what if I have a binary, what's the probability that this binary will have this velocity in A space? Okay? And the actual number density of all binaries across all masses is the integral of this. So, and also the rate of the LIGO rate now is across all these pipes. Okay? So, we calculate this number assuming Chabrier-Krupa IMF. And then once you assume Chabrier-Krupa IMF, you can calculate this f of k. And then you can plug that back into the, you get this equation, and then you can plug back the LIGO rate into it, and you can calculate how many Milky Way binaries there are. And here, Milky Way binaries that are 10 solar radius separated from each other, which is in the Lisa band, we found that there's about a few thousand of them. This is consistent with results from population synthesis model by two actually competing groups, so it's pretty good. So now the question here that I want to ask is, what is the tightest black hole binary in the galaxy? Now you can get this by setting this number equals to 1, and then you can calculate what's the tightest one just by solving for A. For 30 solar mass binaries, this is about 2.5 solar radii. And this, you can calculate what the frequency for this black hole is, for this binary black hole is, and you can see that it is within the Lisa bandpass. So what I want to conclude with is that Lisa gravitational waves is already constrained by LIGO in the sense that LIGO bound is consistent. It demands the presence of at least one Milky Way binary from Lisa. Okay, and I'll just leave my conclusion slide up. Thank you. Sorry?
You say your results are so far consistent with top state calculations. What do you have in mind for the future that would make them inconsistent?
So these calculations, this population synthesis calculations, assume certain evolution channels. However, there are evolution channels, for example, the dynamical cluster channel is not represented in those population synthesis. So we can make tests of different population synthesis models, essentially. So population synthesis goes from one way. Population synthesis, basically the way they work is assume you know how star evolves, and then you evolve the star and you get the LIGO rate. What we do is from the other way around. Assume you know what LIGO is doing, and then see if you can make it match in the middle.
So, do you think the results, or can you expand this framework once there are even more LIGO detections, and you kind of look at the population of all of the estimation parameters of what LIGO is measuring?
Yeah, definitely.
You mentioned that this predicts thousands of Milky Way sources detectable by LISA. How close? Sorry?
Thousands of Milky Way black holes that are 10 solar radius apart.
And therefore detectable.
Well, that depends on the masses.
Okay. So I guess my question was, how close to confusion limit does one reach? In other words, when you have so many, how does one's ability to extract the information from a single event become confused with multiple events?
That's a good question. There is also some confusion regarding cosmological binaries, massive black holes that can hide, that can pretend to be galactic black holes. However, you also can measure the chirp mass. Okay, so there's like other parameters that you can calculate to get rid of confusions.
Okay, well, we need to move on. Let's think.
So I used a different connector when I tested it, and it's not here anymore. So, well, I brought my own adapter, but I used one that plugged in over here before, and I can't see it anywhere. Oh, there it is. I see. Just attach. Okay. So I was expecting like a informal ITC lunch with about 10 people, so this isn't massively prepared. But I thought I would just talk about something which I think is unresolved, both from observations and simulations, which is whether there's a reversal of the magnetic field in the Milky Way. We see some orientation of the magnetic field along the spiral arms in the Milky Way, but there's been a number of papers that find that there's at least one reversal. So this is the sort of most accepted view of the spiral arm morphology of the Milky Way, where you've got one reversal in the sort of in the carina arm. So reversals have been seen in simulations of galaxies, but it's not quite clear what's causing them. Some people put in, some people think it's due to a dynamo, if they've put in some sort of dynamo prescription, or even just feedback might be sufficient to produce a dynamo. So I tried to model the magnetic field with SPH, which is always a difficult problem. There's been various attempts to model magnetic fields with SPH using potentials, so Euler potentials, vector potentials. I used Euler potentials before, but it's difficult to produce complicated field morphologies with Euler potentials. There's some limitations with using that method. And then in some recent work, I instead looked at evolving the field directly. So the problem with SPH is that you need is trying to get div B to be small or zero. So with this method, this divergence cleaning method by Terry Trico, but based on previous work by Dedner, you restrict the divergence of B by damping the div B. So you can write the MHD equation so that div B appears like a wave equation, and then you can adjust the damping term in the wave equation. So I looked at some fairly simple calculations where there's just a galactic disk, so only model gas, and then there's a potential to get the correct rotation curve. There's no star formation or feedback or anything like that in the simulation. The field is initially toroidal, and these are results. So these are with different strength spiral potentials. And what we found that with the field morphology was quite different with and without spiral arms. So without spiral arms, it basically looks like the initial field. It's still toroidal, nothing really happens. But with the spiral arms, we found we got these reversals in the field. If you have weak spiral arms, it's still toroidal, so you needed fairly strong spiral arms to get this reversal. So I suppose my first instinct was that this wasn't real, that there was some sort of numerical problem. So we did things like testing the overcleaning, so that's how you damp the divergence. You can make the damping really strong to get really low values of div B, and testing the resolution, but presuming you used at least we find that with low resolution you did get spurious results, but above a certain resolution we got exactly the same results. So it didn't seem to be dependent on either of those. I did instead also look at where the reversal was occurring, and found that it occurred where there's the greatest velocity change across the spiral arm in the gas, so like where the greatest shock occurred, or at the radius where the greatest shock occurs. So the blue line shows where it goes negative is the reversal, B theta, and then the red line is the change in velocity, and the largest change is where the reversal occurs. So if it is related to where the gas undergoes a strong shock, then the reversal should, you can then change the potential so that the strongest shock occurs at different radii, and then you might expect the reversal to occur at different corresponding radii. And that's kind of what this table shows. If you look at the location, the second column, the location of the maximum velocity is in, as you make it move it outer, larger to larger radii, then that you similarly move the reversal out to larger radii and vice versa to smaller radii. And also the location of this maximum change also corresponds to roughly to the inner Lindblad resonance of the disk. We also see a reversal at co-rotation as well, and you can move this like the ILR outside your disk, and then you get no reversal, and also again with weaker arms there's no reversal. So if this change in velocity is small enough, then there's no reversal. So then the next thing I tried was sort of wondered was whether it would still happen in a grid code. So I did try some simulations with Athena, and I did similarly find a reversal occurring at similar radius, but for some reason I couldn't get the simulations to run much further than that. And reversals also been recently found in another paper using again a quite different code to SPH. I didn't find quite such large-scale reversals. I just found sort of more local reversals. And there's also a recent observation of paper that queries whether the observations in the Milky Way are real. They think that if you allow for the 3D distribution of gas in the galaxies and calculate a 3D map of the magnetic field, then it's not. There's no reversal. And another reason to think that there might not be a real reversal in the Milky Way is that they haven't been observed in other galaxies. So yeah, that's basically. I think. I don't know whether these reversals are real or not, so I'm just interested in whether anyone else does further work to either confirm or disprove these reversals. Thank you. Yeah. Well, I'm always cautious with results of simulations, and particularly with magnetic fields in SPH. You can't be overcautious with them. That's why I tried all the various overcleaning tests and tried running it with a grid code.
I was surprised that the resolution didn't make much of an effect, because you would think, I'm used to grid, not SPH, but as you refine more or less, the shock structure can change dramatically, and then it will affect how it's reversed. So
I think, well, as I say, it didn't depend on resolution. At lower resolutions, we did see that the shock wasn't being resolved very well, and that was causing different results. But once, I mean, like this, when I was saying not dependent on resolution, but when it's in several millions of particles, so that's fairly high resolution. Yes, yeah. I mean, maybe if you had a stronger shock, you would need higher resolution to get consistent results.
Does the Athena, this is also with constrained transport or with divergence cleaning? The results of Athena?
It's not, it's the constrained transport, yeah.
So I think it's at least encouraging that the SPH and the constrained transport are at least agreeing with each other when we look at the reversals.
Yeah.
So maybe could you take the next step and say, well, if you see the reversal correlates with the velocity gradient change, could the observers then take that and where they see reversals,
yeah,
also see corresponding velocity gradient?
Well, in the Milky Way, it is consistent with that, but again, it's only one galaxy, so it's a bit difficult to do a good comparison. I think they're using Faraday rotation. So was there a second question? Yeah, so someone else.
Any other questions? Looks like everything was clear. Thank you very much.
Okay, so can you hear me? Yeah. So since I'm the tallest of all, I think I'm going to stand here. All right, so I just shortened the title. And so I'm going to talk about the local interstellar magnetic field. And by local, I mean this is an image from one of our simulations. I like this one because it's almost like a fossil, the heliosphere in the interstellar medium. And by local, I mean we would like to know what the interstellar magnetic field, the values, orientation outside of the heliosphere. And we would like to know not just a couple of AUs outside, but as you go away, maybe 400 or 1,000 AU, what is the value? So it's an opportunity, when you have astronomical objects, you have, like she was describing, all these difficulties to measure a magnetic field, but here, because we have lots of data, we might be able to constrain the interstellar magnetic field locally. All right. So I just wanted to remind you what the heliosphere is. So the heliosphere is this bubble carved in the interstellar medium by the solar wind. So the sun is here, there's a solar wind, and as we move through the interstellar medium, there is a bubble formed called the heliosphere. And I'm not going to go all the details of the terminology, but what is important is that we have data from spacecraft like Voyager 1 and Voyager 2 in two different locations. So it's only 2 data points in a huge sphere, but we do have local in situ data. And we think, I especially will talk about Voyager 1, that we think left the bubble. So it's measuring locally whatever magnetic field is there. All right, so we knew before Voyager 1 left that the interstellar magnetic field is important. But when you're trying to model that with sophisticated 3D MHD simulations, one of the largest unknowns is the interstellar magnetic field. So you don't really know neither the orientation, neither the magnitude. And you do have, I'm not going to talk why, but you do have lots of constraints about all the other variables. But the magnetic field here, your guess is as good as mine. It's really pretty wild. And we do know that the location where we are is between these 2 clouds, local cloud and the G cloud. We are not certain if we are really at the edge of this local cloud or if we are outside. But perhaps, I'm going to come back to that, what we're measuring outside the heliosphere has to do with this interaction. Okay, so before even Voyager 1 left the heliosphere, we knew something about the interstellar magnetic field. So I will tell you some of the observations that we thought were constraining a little bit. So here's a schematic of the heliosphere. Here's the sun. We are moving through the interstellar medium. And this team, the French team, Rosine Lallemant and collaborators in this paper in 2005, argued that because we are measuring a different direction for the entrance of the hydrogen atoms than the helium atoms, we could constrain the interstellar magnetic field. So the reason is the helium atoms don't really fill the heliosphere. So the heliums that are outside in the interstellar medium stream into the heliosphere like they are not seeing the heliosphere. However, the hydrogen atoms do interact with the ionized matter outside in the local ISM. And because they do interact, they are influenced by whatever interstellar magnetic field is doing out there. So if it's rotating or compressing the density out there, hydrogen will feel it, not helium. So when you detect hydrogen inside the heliosphere, the direction that is streaming towards you, and here is ecliptic latitude and longitude, is in a different point than helium. So they argued in this paper that these two atoms make a plane, these two orientations make a plane called the hydrogen deflection plane. And there is lots of arguments that this plane should be the interstellar magnetic field plane. Okay? In fact, when other groups, including mine, we used different observations of Voyager. Voyager was still inside the heliosphere. We argue that this hydrogen deflection plane is consistent with the distortions we were seeing. So, okay, maybe the interstellar magnetic field is in this hydrogen deflection plane. And in fact, if you look where this plane lies, it's really kind of between the morphology of these two clouds. So perhaps this orientation has to do with the interaction of these two clouds. One thing to notice, and I'm going to come back to that, if you look, this is a cut from one of my simulations, a meridional cut. This is a hydrogen plane. It's 60 degrees away from the solar equatorial plane, that is the plane of the solar magnetic field. It's very different than what the solar magnetic field is doing. So here is a schematic that shows Voyager 1 going through the heliosphere. So if you're inside, you should be the heliosphere, you should see solar field in equatorial plane. And once you're in the local ISM, you should see a field at least 60 degrees away. So this is what we thought about the orientation. What about magnitude? So this is a huge controversy, and I just wanted to summarize in a couple of bullet points what we think we expect the magnitude to be. You know, if you would have asked me maybe 15 years ago, I would have said the field would be 2 microgauss to 3 microgauss. Recently, and this was a couple of works, including mine and others, we argued that the observations inside the heliosphere, Voyager was still inside, are telling us that the field has to be strong, 4 to 5 microgauss. Now, other groups, there is this other mission, IBEX mission, that detect a ribbon that I'm not going to show you here, but it's a feature in the sky. When they try to fit to this ribbon by several mechanisms, they argued field has to be maximum 3 microgauss, weaker. There is some more recent argument that argues that Cassini, it's another data set, should be actually 5 to 6 microgauss, stronger. So it's a little bit of an open door what this field is. Now let me show you some data. So Voyager 1 left Interstellar, the heliosphere in 2012. And what it measures, this is in nanotesla, so just multiply by 10, you get microgauss. So what Voyager measure throughout this period in the interstellar medium, there's some fluctuations, but it's around 4.8 or 5 microgauss. It's a strong field. It's a strong field, and the orientation here, those are funny angles that these people use, but suffice to say that the angles of the solar field is shown here in these dashed red lines. This is orientation of the solar field, solar equatorial plane. The field measure outside vary by really 10 degrees or more from the solar field. It's a solar-like orientation. Has nothing to do with the hydrogen deflection plane. So this was a big surprise, and I just decided to put the most recent hot-the-shelf data. So you can see the magnetometer data. I converted to microgauss. This is until mid of this year. I'm not showing the angles here. The angles are still solar-like. It's still like a solar field. And the magnitude has some variations we think has to do with shocks in the interstellar medium, solar cycle variations, but the average is a strong field, 4.5 microgauss. At least sometimes goes even higher. Okay, so why is that? This is a huge puzzle in the field. And we're trying to understand what makes a field. If we do think that the field far away is in some plane like hydrogen deflection plane, why it's solar right here when we are measuring. So we did notice in our simulations, this is a heliosphere shown in the nose of the heliosphere. You're outside looking straight down the tail in yellow, that the 3D simulations show the same effect. You start with a field far away in the hydrogen deflection plane, and as you get closer to the heliosphere, is showing in a side view, the field rotates to a solar orientation. So we published it. We didn't have a physical mechanism. It was almost like just a numerical result. Why is doing that? So this year, we finally figured out the mechanism that was making this rotation. So this is what I wanted to show you. So what we think is happening, and this is the beginning of this year paper, is that there is reconnection that is happening in the tail of the heliosphere. And the key reason, the key feature of that is that the nose reconnection, the global nose, it's suppressed. For you to really get this global rotation, you really have to have reconnection just in the tail. And the physical reason for that, it has to do with the fact that we are moving through a partially ionized ISM. You have neutral hydrogen coming in from the nose. They do get stripped of their electrons, and they form a very hot population of ions. And turns out, you can look at some classic papers, that you have more hot population at the nose and the tail. So make the tail cold. And if you look at some plasma conditions, this is a favorite location for a connection if you have the same conditions inside and outside the plasma. So it means that we are getting some sense what is causing an object like the heliosphere that is going so partially ionized to reconnect just in the tail and not in the nose. And what this simulation that we did show, and this is a cartoon, that if you have the solar field like that, and you have an interstellar field coming with a really inclined angle, once it's reconnect in the tail, it's gain a solar geometry. You have something that is called tangential discontinuities that make this whole field be solar. So I'm running out of time. I just want to show you the end result, that if you do that and you allow a connection to happen only in the tail, not at the nose, you form a family of field lines that are solar-like for a while. You really have to travel into the interstellar medium from quite some distance to start seeing a different field lines that are highly inclined to the solar orientation. So my last slide is to kind of see if I inspire you to look at other objects, astrospheres or galactic bubbles or others that go through a partially ionized ISM. They should have a similar effect. They should have a favorable locations where a connection will happen. And we'll rearrange the field line ahead of it. So it can suppress instabilities, all sorts of other effects. And what is nice, we did two types of simulations, one with no reconnection, left, and this is with reconnection. Without reconnection, the field continues in the hydrogen deflection plane, highly inclined, just drape around. But if you allow reconnection, the field rotates dramatically to a solar orientation and stay like that for a while until it rotates to the hydrogen deflection plane. Thank you.
I believe that there is an easier explanation why you have fast reconnection in the tail compared to the nose. Because where would you have a higher level of turbulence? Definitely the tail, not at the nose.
It could be.
This is the prediction of the turbulent reconnection theory. We don't need the fact that all this fancy plasma effects to explain reconnection on the scales, which are much, much larger than the corresponding plasma scales.
It could be, Alex. This is one of the other reasons that could be. The solar magnetic field is like a flux drop, is very unstable. We're still trying to characterize this turbulence. It could be playing an important role, but even without you still, understanding this turbulence, in the simulation it's appear, but you still need to kind of figure out what is really driving this turbulence. There is this effect that the thermal.
If you are moving through a fluid of a high Reynolds number fluid, you are automatically gaining turbulence in the wake. If you are even running, you have the wake of turbulence after you. So you don't need fancy plasma effects, plasma instability.
I think that the trick is in the quantitatively, because if you're just going through Reynolds number, the turbulence will happen really down the tail. This is happening. You need to have enough time for the alpha speed to communicate back to the nose. So you need it not that far in the tail, but you do have turbulence because the tube is unstable. So we can maybe talk offline on the details. You do?
Any flow that gets turbulent in the wake.
So then you have a testable prediction here that eventually the field lines through changes. So how long is it going to take Voyager to travel that?
So it's again, this is a quantitative issue. This is a simulation with a uniform solar wind. If you have solar cycle, it's going to push this rotation region a little bit farther away or farther in. In this paper, we predicted that in the next 3 years, in a static simulation, it's going to see it. And it should be dramatic rotation. Now, this is static. I will add, I don't know, usually with solar cycle, it's at plus or minus 10 AU. So you are adding 2 years plus or minus. But it should be something that Voyager will measure. Not so bad. Yes. Yes, I have it already, so it's good.
My question was very similar to Ito's, and I guess one other follow-up, could you predict how quickly the angle will change?
Right. So we do have, I didn't show it here, we have a cut along Voyager 1 showing how the angles are going. It's a very narrow region. And we've been talking to the magnetometer people to see if you guys see a very strong rotation. Yes.
Is your hydrogen deflection plane the galactic plane?
No. It's actually 60 degrees from the galactic plane. Yes. It's pretty large. Right, it's pretty large. It's pretty large. So it's also, again, the importance to really understand the draping, to really say, is this magnitude due to the compression of the field, or I can say that at infinity, it's that. And in this simulation, at infinity, I'm putting a pretty large field. Yes.
Very much,
Okay, thank you, Avi, for inviting me. It's an honor to stand here instead of Rai Weiss, although I still have to get my Nobel Prize. So I'll be talking about a few works that we did with Avi and one paper that just came out with Dan Lorimer on fast radio bursts. Of course, it's a very young field, but we are trying to build the cosmological models and see how, if all of these events are cosmological, or at least subpopulation of them, how can we constrain properties of sources. So just to summarize, there are only 25 events that are publicly available. And their origin is still a mystery, although there are few telescopes that now observe these events. There is one FRB observed by Green Bank telescope, 17 by Parkes in Australia, 5 by Atmos, 1 by Arecibo, and 1 by ASCAP. So it's really nice that there are different detections in different parts of the world observing these fast radio bursts, and also at slightly different energy bands. So from 0.7 gigahertz to almost 2 gigahertz. At least one of these events is cosmological. As we know, the repeater FRB 121102 shows multiple repetitions, and I'll mention a bit more about this event in a second. So the properties that we know so far is that these are very fast bursts of few millisecond pulses in radio. They're bright, and the peak luminosity is a few Jansky, up to 30 Jansky for the first detected Lorimer burst. The central frequency is around 1 gigahertz, and the dispersion measure, which tells us what's the integrated electron density along the line of sight, is varies from 200 to 2,000 parsec per cube centimeter. So these places, if they are all cosmological, places fast radio bursts out to redshifts roughly 1. The rates are very unconstrained because there are only 25 events known and roughly fall in the range 1,000 to 10,000 events per day per sky, so it's pretty high rate. Number counts were recently shown to be inconsistent with a flat luminosity function. So, for example, here in McCartan-Eckers, they show the slope of the integrated number counts as a function of sensitivity or fluence of the event. And it's roughly inconsistent with a flat distribution. It's steep with a slope of around -3 for the integrated number counts. And as I said, one event was shown to be cosmological. It was localized with high precision, and we heard talks about this event here. The galaxy is located at redshift 0.2, and it's a very small metal-poor galaxy. So it's very strange why this event was localized to be in such a rare galaxy at low redshifts. So most information about these events can be found in the online catalog, which is currently and always is being updated. So there is information about the flux, the dispersion measure, location of the events, and the measurements by each telescope. It's a very handy catalog. So of course you can be skeptical and say that it's a very poor statistics, and the origin is still unknown. How can we do any cosmological constraints with this population? But still we find that it's very useful, even based on these events and using our best cosmological models that are available, to make predictions for assuming different luminosity functions and sources for these events, and propose new tests for observers and guide observations. And we are now collaborating with some people from ASCAP to test our models. So these are just few first steps in the field, which is really young. So recently, actually, we had a press release for our paper with Avi, where we showed the number counts as a function of the sensitivity for future telescopes using different cosmological models. All models were equally normalized to the detected events, and then we took them to higher redshift populations and showed that for any actually scenario, we expect to see many more events once the telescopes become sensitive, such as future square kilometer array. So to summarize this paper, I just want to know that for all models for the SK, we expect to observe more than 10 to the 5 events per day. So if SK will have a large field of view and is supposed to detect many of these events, if they are cosmological. Then we found that actually the spectrum of the fast radio bursts has large effect on the detected events. For example, here on this plot, I show the rate of FRB as a function of sensitivity of the telescope for few models. So solid lines show the Gaussian spectrum, such as of the repeater. Dashed lines show that if the case when the spectrum is flat around the frequency. Blue lines are for the Schechter luminosity function, so it's a luminosity function where we have a considerable faint end population. And the red lines are for the standard candles where the luminosity doesn't vary and it is just constant. So first of all, in all the scenarios, the total number of events, when you have enough sensitivity to integrate, is very high, again, above 10 to the 5. And you see that there is strong effect of both the spectrum and the luminosity function. So both parameters are very important. What's interesting is that if you have a Gaussian type luminosity spectrum, then SKA would observe FRBs only from a particular redshift range, because otherwise they would redshift from the band. And then SKA will have 3 different instruments in 3 different frequency bands. So with SKA mid, we would be able to observe FRBs from redshift 1 to roughly 3. SKA mid 1 would go to redshift 9, and the SKA low would observe events at redshifts higher than 9 if, of course, they are bright enough. So these results assume that the universe is kind of homogeneous and isotropic. But of course, we know that it's not the case, and there are galaxies and clusters of galaxies. So with Avi and Dunk, we asked the question, what happens if you observe cluster of galaxies that is nearby compared to an empty beam, a random line of sight in the universe. So for example, here we see a coma cluster with high concentration of galaxies, and then there is a random beam where the galaxies are randomly distributed. So is it actually better to focus on a cluster rather than on a random line of sight? And we found that the result is very dependent, again, on the model assumptions, on the luminosity function. So we compared, again, Schechter luminosity function versus standard candles. It depends on the spectrum, again, if it's Gaussian or flat, and also mildly on progenitors. So here we considered young versus old stars that source FRBs. So as a proof of concept, we took a Virgo cluster that is located only 16 megaparsec away from us. It's a very rich cluster, having 1,500 of galaxies. And we found it to be a great candidate. First of all, it's close, and if we have enough beam resolution, we can probe and localize FRBs shown on this map. So this is a distribution of galaxies, of FRBs from Virgo cluster. And also, if we compare number counts or FRB rate from Virgo versus a random line of sight, the expected numbers depend again on the model. In particular, it's good to use Virgo if the luminosity function is steep. So if we have many faint FRBs, we will have much higher rates from cluster than from a random line of sight, just because cluster is very close. And when we integrate over the luminosity function, we get all the faint events from the cluster, while in a cosmological beam, faint high redshift events are way below the sensitivity of the telescope. However, if the luminosity function is flat and we have standard candles, there will be no difference in FRB rates from cluster or from a random line of sight, and all cosmological events will contribute. So comparing two beams, one which contains cluster and the other which doesn't, would tell us if there is considerable population of faint FRBs or not. Then there is some effect of spectrum. If it's Gaussian, then again the telescope will see particular redshift or particular cluster, and then again it's better to observe a cluster or clustered region rather than an empty beam. However, if we find that the nature of progenitors in this case doesn't make any strong effect. So now we can actually take any map, for example, SDSS distribution of galaxies around the sky, cosmic web, and just compile a map of fast radio bursts distributed around the sky. 1 minute. And we actually took two catalogs, 2DF and SDSS data release 7, and for the both of them, there is a library of clusters available, and here I present the number of expected rates as a function of distance of clusters from us. Each color shows the entire catalog, but for different cosmological assumptions. So blue colors here show the case when we have a lot of faint FRBs, and this horizontal lines show the cosmic mean background rates expected. So in the case when we have a lot of faint FRBs, all clusters yield much stronger rates than the mean cosmological contribution. Two black and magenta here are for the case of standard candles, so when the luminosity is fixed and there are no faint FRBs. In this case, we expect less FRBs from clusters than from mean cosmological contribution. So just two random beam and a beam with a cluster inside would give the same results. And here the red and gray are the Schechter luminosity function, but where low luminosity cutoff is matched to the least luminous observed FRB. So in this case, there are scenarios in which clusters win over cosmological background, and in other cases, they don't. So it's really interesting to see what observations will tell us. Okay. And we also show a list of the best candidates to look at from these catalogs, and we find that there are few best sources. First is the ones that are really close to us, such as Virgo. Then rich clusters located in the intermediate distances between a few hundred megaparsecs to roughly a gigaparsec are also good candidates, but also poor clusters located in the window where actually the cluster size matches the beam size of the telescope, and thus all the sources are within the beam could also be good candidates. So you can find all this information in the paper or talk to me. Thank you very much for attention.
Cluster with parts or something like that?
So it's the sum of the two, right? It's so depending on cosmological model, for example, the gray dots, to get the absolute total rate, you need to just sum the. If you're looking at a cluster, then you need to add the cosmological background plus the rates from cluster. If you're staring at the random field, then just the cosmological mean. Yeah. Right, it's for beam of 1 degree.
Order unity.
Right.
Other questions for Professor? If not, happy Thanksgiving to everyone.
Yeah.
Now I know what you're doing.
Well, it's just one line of project.
I know, but you know, I have to start slowly
Yeah.
because you're doing so many different things.
Was it?
Very, very understandable.
Okay.
Yeah.